So today's talk will be on embodied multimodal intelligence with foundation models. So what do I mean by this? So the goal that my research is aiming to achieve is to build generalist robot policies that enable intelligent autonomy in a variety of applications and systems, ranging from home assistant robots to search and rescue, autonomous inspection, and so forth. And this is particularly exciting for me because it forces me to think about the challenges and the opportunities in building robot systems outside of a lab environment, and really think hard about how we can build algorithms and methods that can work for any robot in any scenario, even if the environment might be unstructured, as you can see from some of these videos that come from some of my past works on robot learning. So the canonical approach I'm taking towards this goal is inspired by advances in other areas like NLP and computer vision, where there has been this kind of paradigm shift in which we have seen that large models trained on diverse data sets typically surpass specialist models tailored for specific tasks like object detection. You know, we have like RCNN, RCNN and all the series, or like recurrent neural networks for language translation and so forth. And so the workflow for developing these models, for example, in NLP, is that they train these models on large diverse data sets that can not only do one single task, but many different tasks like code completion, question answering, translation, etc. And these models then typically outperform single task models. If we look at some of the most impactful advances in robot learning in the last couple of years, we have seen really tremendous progress in performing dexterous tasks by methods like, for example, ACT or diffusion policies. However, these approaches are kind of specialist models that work really great if you want to fit to a single task, but do not really scale very well in order to learn generalist robot policies, as you would typically need to retrain these approaches for each and every task that you might want to perform. So the North Star of my research is to build a novel workflow for robotics by building generalist robot policies that can control many robots in many environments and can perform tasks while working with and alongside humans. And so on the path towards developing open world generalist robots that actually work, I have looked at what it means to have a foundation model for robotics, where we might get the data from, and how we might train these models to control multiple different robots, and inspired by recent progresses in foundation models of vision and language. My research has also studied how we can build this pre-trained backbone for robotics and then adapt it for downstream tasks. So therefore, I can envision a future in which you can download your favorite robot brain online, and then out of the box, your robot starts showing intelligent behavior in a reasonable and useful manner for any type of robot. So let's talk about the key ingredients that we need for developing generalist robot policies, and what are some of the differences and challenges in applying the same recipes that have worked in other areas like NLP and vision to robotics. So let's start talking about the obvious one. In robotics, we don't have the luxury of readily available large data sets that we can download and train on, since robot data is typically scarce and expensive, as it usually requires human supervision in order to collect this data. Additionally, robot data is highly multimodal and heterogeneous, as instead of only training on natural language, discrete kind of tokens, we have like several sensing modalities that our robots need in order to interact in the physical world. And additionally, every robot will typically have different observation and action spaces, right? One more constraint that we have in robotics is that we typically need real-time control. So this means that we typically need to run these models with high frequency, and so we cannot really wait for a minute until the ChatGPT API returns a response before we decide what our next action should be. And finally, as we develop models that can perform many tasks in many environments, we also need better ways of evaluating those, because the more capable your model is, the more evaluations you will need to run in the real world, which is something that's very tedious. So I will talk a bit about all the three ingredients and the research that we've been doing at Berkeley to try to advance some of these challenges. So let's start with the data side. Where do we get the data to train these generalist robot policies? Because no matter what the embodiment is, collecting robot data is inherently expensive, as we typically need to teleoperate a robot to collect data for each and every single task that we want to learn. And I speak from experience here. Here you can see me collecting teleop data during my PhD in Freiburg. So this is why my research has focused on leveraging existing sources of data across existing embodiments. There have been some previous efforts to collect data sets for specific embodiments, like Bridge v2 or RoboNet, RoboTurk, and so on, but typically not usually in a format that allowed that was very compatible with each other and did not really allow to co-train on all of these. The key insight here is that every robotics lab in the world typically collects some sort of data to support their research. And because this research might be tailored to that specific lab's research, like maybe it's like tactile sensing or long horizon behaviors, or maybe like it's like deformable object manipulation, etc. We typically don't upload this data and make it available for others to train on this, because it's kind of small and niche, right? So this would be like this kind of smaller bubbles around here. So while I was wrapping up my PhD, I was able to collaborate with Google on this project called the Open X-Embodiment dataset, where we essentially ask all our friends, well, sorry, something happened here. Where we essentially ask all our friends if they have existing robot data, and then we aggregated it, all of these diverse data sets, into a common format that enables training on them. And we ended up with over 1 million of real robot episodes. It was substantially more than any robot data set, and the data set contained not only a single robot embodiment, but up to 22 embodiments, and over 34 labs in the world participated in this large effort. Regarding the results, this was the first time we saw sparks of a single model trained on multiple robots across multiple data sets, surpassing the best previous method that was tailored for that particular setup. And personally, I was one of the 5 researchers, and the only one in Europe, that contributed continuous evaluations during the model development with the robot setup that I built during my PhD in Germany, which you can see here on the top. This paper has been quite impactful because it has allowed really algorithmic progress on the modeling side of training generalist robot policies, by making it possible to train on over 1 million of diverse cross-embodied data for the first time. And most of the works I will be presenting in this talk will use this OpenX embodiment dataset as their basic foundation. Okay, so far we have talked about where we can get the data to train a generalist robot policy. But even if we now have such a large heterogeneous diverse data set, how do we make use of this to train models? How can we model this very multimodal heterogeneous data distribution? Because this is really easier said than done, as there is a general lack of shared interface, right? So different robots have different kinds of task specifications, different types of sensors, different number of cameras, different action spaces. And so essentially figuring out how to share information and knowledge across robots and tasks that may look so different makes this a very hard problem. So let's start with a basic example. When we typically train a robot policy, the model takes usually an image input, like a current image observation, and a task, which nowadays is usually a language instruction, such as pick up the spoon here. And then the model will predict a sequence of actions, like end effector poses, for example, to achieve that particular goal. And now our premise is that we want to fit our model on a large, diverse, heterogeneous robot dataset. Now, if we squint a bit and we replace the robot image with a more regular, like internet image, like, for example, the Statue of Liberty, and the instruction with something like caption the scene, you know, this starts to look very familiar to kind of like a vision and language model, right? And so essentially, the key idea in the works that I will now show build upon is that we can view robotics, like the robotics problem, as a similar problem, where we are trying to learn a powerful model that maps from images and instructions to answers, just that in our case, the answers are not text, but they are robot actions. So this means that we can formulate this problem as a multimodal sequence prediction problem where we have language tokens, image tokens, and action tokens. And the advantage of this formulation is that this now really allows us to also leverage many of the advancements that have been made in the non-robotic domains for multimodal sequence modeling. So as a first step towards developing generalist policies, and also one of my first works during my postdoc, we developed Octo, an open source generalist policy, where we trained a large transformer-based policy on around 800,000 robot trajectories of the open X-Embodiment dataset I covered before. And we did this by tokenizing all these diverse heterogeneous inputs and action outputs. So how does it work? The Octo transformer is a fairly straightforward transformer model. So it has a pre-trained language encoder that tokenizes your language inputs, and then it has an observation tokenizer that takes care of image style inputs by patchifying them and running them through a shallow CNN to produce image tokens. So now the observation and task tokens are concatenated and fed into a large transformer, which looks quite similar in our case to a vanilla vision transformer architecture. Additionally, we defined as purple readout tokens, which are kind of placeholder tokens that summarize the embeddings and that then go into functional heads. And one thing to note here is that we trained a model with goal-conditioned behavioral cloning, meaning that it learns to predict a sequence of actions to reach a goal state given the current state. And this formulation also helps encode flexible ways of specifying goals, such as using goal images or language instructions. Okay, so we have now the task, observation, and readout blocks. And since this is a sequential model, this will also happen over multiple time steps. Maybe one thing to note here is that the functional heads in our case consist of a diffusion decoding head, because we found that diffusion really works well for this kind of continuous multimodal action distributions. We divided the evaluation into zero-shot evaluations and fine-tuning evaluations across many institutions where we used the same fine-tuning recipe to adapt Octo to new sensory and action spaces. And we found that in experiments across 9 robot setups, that Octo could outperform, Octo could control multiple robots out of the box and outperform previous models from Google trained on similar data. And now I want to show this video. Oh, I think I muted myself.
Oh, one success, nice. One success. All right, good.
Maybe I'll play it once more, but
Bam.
One success, nice. One success. All right, good.
So this is the this is a video that shows the first time we deployed Octo on the Google robot. The first time it actually worked and, did like a meaningful pick and place task. And, we were like super excited that, it actually worked. So here we kind of reversed the roles a little bit. So for the OpenX project, I was doing evals for models being trained by Google in Mountain View. And now here we developed this model set in Berkeley, and we asked our friends at Google if they could do some experiments and evaluate Octo on their robot, since we trained on their data. One thing to note is actually that this is kind of like a hard evaluation setup, because we trained on data from the Google robot that was recorded in a different building, and then they moved their lab to a new building. So it was kind of, out of distribution, and, it's nice that it still worked, even though like everything was kind of new. So yeah, we were super excited to see that, zero-shot evaluations work. Okay, so these were zero-shot evaluations, but one thing I want to highlight is the adaptability aspect, because ideally the model should be useful for your robot, even if we did not pre-train on it. It's possible that for some tasks you might want to use like force torque sensors, or you have more cameras, or you want to do joint control, or and ideally like this should be still useful. So this is quite easy to do with Octo. So if you have a new input, like let's say force torque readings, you can slot in this new input with a few tokens and then fine-tune the model, and you don't need to throw away the pre-trained models. And because most of the parameters are inside the transformer, you get to retain much of the pre-trained knowledge. So I will not go into the detail of the fine-tuning results, but essentially we found out that the representations learned by Octo, or like a generalist robot policy, work much better than state-of-the-art visual representation learning techniques like R3M or VC1, etc. And in terms of impact, Octo has become quite popular, becoming one of the most downloaded robotic models on Hugging Face. And we actually see that researchers around the world find it useful for fine-tuning. So this is a video I found on Twitter from a researcher that fine-tuned Octo with around 50 demonstrations on this cross-embodied spot robot, which is an embodiment our model did not see during pre-training. And more recently, we noticed that there is this Japanese company called Tokyo Robotics that is using Octo to drive their humanoid robot. So that's pretty cool. That the model is being is useful also for other researchers and companies. Okay, so far I have showed how you can train a generalist policy on a diverse data set containing a bunch of single R manipulators. But if you think about this for a second, like how generalist is this really if all it can do is single R manipulation, right? Because robots come in many more morphologies, right? And as I mentioned before, there exists a lot of more robot data that we could be learning from, like self-driving cars, like quadrupeds, humanoids, etc. And this is also important because there is this potential for transfer from all these different embodiments, right? So for example, navigation data might transfer to drones learning how to avoid obstacles, for example. And obviously, like we are not the first ones to have this idea of trying to use data from different looking robots to train like single policies. And related work has already shown signs of transfer between, for example, egocentric manipulation and navigation, but in a way that is not really like scalable because it requires somehow like manually aligning different action spaces, for example, or only using like wrist cameras. So this is why my research was focused on developing a more scalable approach that can learn kind of from any robot embodiment. Concretely, in this project, we added more embodiments such as bimanual manipulation, locomotion, or navigation to the data mix we originally trained Octo on, and for a total of, I think, 900,000 trajectories. And then we trained a big transformer, but now with embodiment-specific heads on it. And we call this model cross-former, and this model accepts, again, variable observation inputs and predicts variable action outputs, which is important, for example, to predict chunks of different lengths to account for embodiment-specific control frequencies. Because here, like we have like robots that do like 5 Hertz control, like the Widow X, to like the bimanual Alohas that can do like 20 Hertz or 50 Hertz control. Yeah, and so most importantly, this model can now consume kind of data from any embodiment because we don't need to manually align the action spaces. And one key design decision is here also to try to maximize transfer across embodiments. We also try to maximize parameter sharing across embodiments. And here are the rollouts from our model. And as you can see, we evaluated like really challenging tasks such as indoor and outdoor navigation. We have like really dexterous bimanual, like sushi cutting tasks. We have quadruped locomotion, drone flying. And I want to highlight that all the rollouts you are seeing here come from the same model checkpoint. So it's not like we cherry pick, like, okay, this particular checkpoint works best for this embodiment, or so this is all the same set of neural network weights that are controlling all these different robots. And regarding quantitative results, we found that our cross-embodied policy either matches or outperforms specialist policies trained for specific embodiments. So also there is some kind of like, spark of transfer as we have seen in LLMs or like in NLP and vision. And cross-former has been quite impactful despite being a fairly recent paper by receiving broad attention from media and also industry. And it additionally has enabled a spur and follow-up works in cross-embodied generalist policies, such as this work from physical intelligence, for example. Okay, so at this point in my talk, you might be wondering, okay, this sounds cool, and is then essentially scaling cross-embodied robot data all that we need, right? This would be like a fairly straightforward conclusion to make. And I believe the answer is no. Why? Because even if we develop robots capable of many tasks, this isn't going to be very useful if they cannot reason intelligently. So for the models I have shown so far, if the policy face like an unfamiliar situation that's like out of their training distribution, they have no mechanism to intelligently solve it. And so if we look at LLMs, for example, they have been pre-trained on all of the internet, right? But even after seeing all the internet, they are not able to do all the tasks we want them to be doing, right? So nowadays, people in LLM land, they are training specifically for reasoning, like you have, maybe from like DeepSeek or like the latest like O1 models from OpenAI, etc. And this is because reasoning are essentially the compositional bits that can be reused and transferred to solve with existing knowledge. And therefore, this is also like what we want to be doing for robotics. We want to have the ability to reason intelligently. So now, because we are formulating robotics as a multimodal sequence modeling problem, and we are kind of transferring many advancements from LLMs and VLMs, like model architectures, training objectives, and so on, the question is, can we also transfer some of the algorithmic improvements that have helped LLMs and VLMs generalize, such as the idea of chain of thought reasoning, meaning that we make the models reason before predicting the answers. And so to this end, we have recently released embodied chain of thought, where we make these models reason through the task at hand and the next actions it's supposed to predict before actually predicting the next action. So instead of mapping directly from images and language to actions, as you can see in this example, in the video, we perform embodied chain of thought reasoning steps before predicting the actions. And I will explain how this works now. So the idea is simple. As we want to maximally use the robot data that we already have, we can use now internet scale foundation models to annotate our robot data by generating semantically grounded reasonings like subtasks, predicting bounding boxes of the object to interact with next, or traces of how the gripper is going to move in the future, for example. And now the core idea of embodied chain of thought is to train an autoregressive vision language action model. So this is a VLM backbone that is fine-tuned to predict robot actions. By making this model predict this intermediate grounded reasoning steps before predicting robot actions. So essentially, this means that we force the model to think carefully and look carefully before acting. And this green boxes over here represent semantic reasoning steps. So these are essentially similar to chain of thought reasoning in LLMs. It's like happening in language space. But more interestingly, this purple boxes represent visual reasoning grounded steps. So these are like predicting the bounding boxes, or these are happening in image space. So this is why it's not only like reasoning in language, but also visually. And we evaluated our models across really challenging out-of-distribution tasks like spatial relations, unseen objects and tasks, and found that this resulted in a 30% performance boost. So this is the same model, OpenVLA, trained on the same data without reasoning. And so this embodied chain of thought is now the same model with the reasoning. And this is Octo that I showed before, and RT2X is a model, a much larger model. This is a 55 billion parameter VLA from closed source from Google. And our model is, this one is 7 billion parameters. So even though it's much smaller, by doing this reasoning and thinking, it's able to outperform all these other models. And now, I think the cool part is that not only does embodied chain of thought improve performance, but it also makes the policies more interpretable, because now you can see what the model is thinking of doing. It also makes the model more interactive, because it allows now for humans to correct the behaviors by editing the reasoning chains online. So in this example, for instance, we asked the robot to pick up any object that is not yellow, and it predicts the wrong subtask. And we tell it that the eggplant is purple, and then it predicts that the eggplant is a non-yellow object, and that should be picked up and makes the correct plan for it. To finish this part, one of the coolest experiments in the paper is essentially we trained this model with reasonings from a single robot, this like Black Sheep Widow X robot that you have seen so far. And then we asked the model to predict reasonings for unseen embodiments that are part of the OXC dataset, like the Google robot or like a Franca, etc. And so now, to my very big surprise, because I never thought like this experiment would work, because we'd never seen this data before, when you ask the model to predict the reasonings for these robots, they actually make a lot of sense. Like, you know, it's predicting the right objects, semantics, it's predicting the right trajectory that the gripper has to follow to pick up the banana here. And so this really suggests that embodied chain of thought is a good way to scale and transfer robot reasoning capabilities between different robots. And this paper also has been quite impactful by becoming a new standard to train VLAs with reasoning, because essentially it allows to leverage better the VLM pre-training, right? Because like these reasonings are very similar to a lot of the in-distribution tasks that the VLMs have been pre-trained with. Okay, so far I have showed how you can build generalist policies that rely mostly on visual perception, but one can only go so far with vision only, as you all know. In this example, for instance, if you ask the robot to, for example, grab a ripe tomato from the shopping bag, it first cannot see really anything inside the shopping bag. And it also would need to use touch sensing to determine like if the tomato is ripe, right? Like it cannot only use like color. And I try to recreate this task with some of our pre-trained models I have been showing so far. And you know, like they fail kind of spectacularly. Like on the one hand, there is like a lot of self-occlusions. It cannot really see like what object it is grasping. And yeah, this really like tells us that, you know, vision only might not be enough to like solve all the tasks we want our robots to solve. So the question is, because given that interacting in the real world is a multi-sensory experience, how can we best enable reasoning jointly over multiple modalities, like let's say vision, touch, or audio, for instance, given that we might have like data scarcity for many of these sensing modalities, right? Like we don't have enough touch data to like train a foundation model on touch or anything. So I believe that leveraging natural language as a bridge across modalities is one possible solution. And in this work that we will soon present at the ICRA conference, we propose a new recipe for fine-tuning generalist policies like VLAs that I've been showing so far on heterogeneous sensor data like touch sensing or audio that really unlocks like new cross-model reasoning abilities, such as asking the robot to grasp the object that feels like a pineapple but is brown when referencing a pine cone, for instance. So how does this work? First, during the fine-tuning phase, we slot in new observation tokens, similar to how we were doing this for Octo in the beginning. And now during fine-tuning, we propose two new auxiliary losses, in addition to the behavior cloning imitation loss. So first, there is a contrastive loss that maximizes mutual information between views and semantics of the same scene. And this is kind of like a clip style loss. And second, there is a language generation loss to predict high-level semantics across modality combinations with a cross-entropy loss. So for example, this would be like equivalent of it, like the robot is grasping something inside a touching bag, a shopping bag, and it has to like describe what it feels in language, given like the tactile or touch input. And doing this fine-tuning recipe really enables our policy to perform challenging manipulation tasks that require joint reasoning over vision, touch, and sound in a zero-shot setting. So these are all like unseen objects, enabling like multimodal prompting, generation of object descriptions upon touch, as I was saying before. You know, like once it touches, like it predicts like, oh, this object feels corded, and also compositional cross-model prompting, like grab the object that is the same color as the button that is metal, for instance. And yeah, and this is really important because maybe like I didn't mention before, but essentially, like if you do like naive fine-tuning without like this proposed recipe, because these policies have been pre-trained on vision, they will tend to ignore like any additional like modality that you input if you don't do like this language grounding scheme. Okay, so at this point in my talk, you might be wondering, yeah, I understand now how we can build cross-embodied generalist policies with reasoning abilities. And, you know, we have been mostly pushing along the generalization axis. But the robots that we have shown so far are not super impressive, right? They are kind of doing like simple pick and place tasks, like with 5 Hz control or something. And ideally, we also want our robots to be dexterous. But dexterity and generalization have somewhat like different ingredients for success, right? Because to push dexterity, you need like high frequency control, which is a little bit at odds with like deploying large models at test time. Whereas to push generalization, you also need methods that leverage foundation models, and also mobility to expose your robot to like more diverse environments. So if you remember, when I was talking about the cross-former project, I mentioned that we typically need to predict large action chunks, so many like future actions in a row, to support high frequency control. But this really starts now to become really difficult once you start training autoregressive like vision language action models, because the tokens of these sequential actions with high frequency are very similar. So what happens is that with like the naive kind of action tokenization that we typically use for training these models, the correlation between these tokens increases and the information per token decreases. Right? This is kind of like understandable, right? And this essentially hinders learning. And you can see here what happens if we increase the control frequency, like after 10 hertz or 20 hertz, like it kind of really is like dropping the success rate like tremendously because of this problem. So the obvious solution is to do some sort of compression, right? Because okay, we have too many tokens. There is not enough information between them. They are too correlated. So let's do some sort of compression for this. So how can we best compress robot data? In LLM land, people typically use byte-pair encoding, which works really well for discrete domains, but not so for continuous robot data. And the other alternative of using VQ-learned representations is kind of complex to train. So our main idea here is that we, when we tokenize actions for VLAs, we use something called discrete cosine transform, which is a widely used technique for continuous signal processing, so continuous signal compression, that essentially uses JPEG compression. So this makes tokenization much better because now the same action chunks require fewer tokens and are much more information dense, leading to much more effective training. I won't go into the detail of like how exactly everything works, but that's kind of the main idea. And now when you apply this technique, you can see on the left that the performance doesn't degrade anymore when once you start increasing the control frequency, and also it enables training autoregressive VLAs 5 times faster than diffusion-based VLAs. And one of my favorite results is that we deployed now this VLAs trained with this technique in unseen kitchens across like Berkeley, Stanford, and UW, so in University of Washington. And this kind of was the first time that we saw like real like zero-shot language tasks like generalizing to completely unseen kitchens. So this was really cool. And at the same time, it also allowed to do really dexterous manipulation tasks at physical intelligence, such as like really complex bimanual manipulation tasks like laundry folding at 50 hertz. So essentially pushing alongside both axes of generality and dexterity. And we have also open sourced a universal tokenizer on Hugging Face, which supports a wide range of different robot embodiments. So if you think that you're interested in doing higher frequency control with a different embodiment, like it might be interesting to check it out and see if you can if it works also for you. Okay, so far I have talked about the data and the modeling side of generalist robot policies. But last but not least, I want to talk a little bit about evaluation. Because evaluating general policies is really expensive. And if you have ever done evals for like real world evals for one robot and one task, you know what I'm talking about, right? Because people bump into your cameras, grippers get stuck, and motors get damaged, and it just takes like a really long time to run evals in the real world. And so one way to get around this is using simulation. as this makes research much more accessible to people who might not have the same setup as you do, and also makes the numbers more reproducible. This is why during my PhD, I developed Calvin, which was kind of the first public benchmark for instruction, like long horizon instruction following from high-dimensional inputs, in which like a single agent had to solve complex manipulation tasks by understanding a series of language instructions in a row in unseen environments. And this has been quite kind of like a really well-established benchmark for generalist policies that's been used both by industry and academia. I think one of the coolest things I have seen with this is like in Munich, some students thought that this benchmark was like so nice that they decided to build a real world replica of the environment. And like this takes like I don't know how many robotics there is, but there is a lot. It takes like quite an amount of effort and time to do so. I think for myself, my PhD, I spent like 1 year or so doing this. So that's like super cool that they thought that this benchmark is so nice. They want to do like sim to real projects with it. But what if your policy is trained on real world data, right? Because like all the generalist policies I've been showing so far are mostly trained on diverse data sets. As I said before, during the development of Octo, we learned in a painful way how hard it is to do evals for like models that can control so many embodiments and do so many tasks. So this is why we started a parallel project called Simpler that tries to leverage sim evals for policies trained with real world data. So the hope is that if we can find a way to evaluate our real world policies in simulation in a way that informs us about how they would perform in the real world, well, then we can just sit back and enjoy life while we run a large number of evals in simulation. Okay, so this sounds great. And not only do the success rates in real and in Simpler have like a lot of correlation, but this actually also holds true, very importantly, for many distribution shifts like textures, camera poses, and distractors. So how does it work? Well, the first step is to mitigate the control gap to ensure that the policy actions executed in simulation yield comparable effect on the robot's end effector as those observed when executed on the real robot. And you can do this by doing a system identification procedure. And the second step, as you have probably guessed, is to minimize the visual distribution shift by trying to match the simulated visuals to those of the real world. And to do so, we apply green screening and also texture matching. And maybe one thing to note here is that Simpler doesn't give you absolute performance correlation. So if in sim you get like 50% success rate for one task, this doesn't mean that you will get the same success rate in the real world. But it essentially, if you have two policies, A and B, and policy A performs worse than policy B and Simpler, this should also hold true in the real world. Simpler has become quite popular, maybe because it has become like a daily driver also for us in our lab and many other labs to develop this generalist policies. But maybe it has become even too popular because we see that now entire VLA analysis papers are being written with just like 18,000 rollouts in this simulated environments, but no real robot experiments. So I think it would be good if they try to also do some amount of real world experiments. Okay, to recap and finish, I have presented. I talked a little bit about the ingredients to develop generalist robot policies. I first talked a little bit about how we can use existing sources of cross-embodied data to train cross-embodied policies that can control many different robots and also learn representations that are adaptable to unseen robots or observation and action spaces. I have also talked about how we can endow our robots with intelligent reasoning abilities, which I think is something very important. And I also have presented one way how we can bridge the gap between this pre-trained generalist policies being like kind of vision only to them like leveraging all the different like sensor modalities and heterogeneous modalities that we might use with our robots, like touch sensing or audio. And finally, I also talked about how we can democratize research in this area and also make like numbers more reproducible by leveraging a real-to-sim evaluation framework. To finish, for the future, I'm really very motivated by developing intelligent assistant robots that can perform tasks for and alongside humans in unstructured environments for really extended periods of time, ideally 24/7. And the 4 key ingredients that we need are advances in dexterous mobile manipulation, intelligent embodied reasoning, lifelong learning, and rapid adaptation, which essentially encompasses the whole life cycle of intelligent autonomous robots. I have many ideas alongside these axes, and if any of you are interested in these directions and would like to collaborate, feel free to write me an email. With this, I want to finish by thanking also my fantastic collaborators, without whom much of this research would have not been possible. And with that, thank you for your attention, and I'm happy to take any questions.
There is a question on Zoom. Sure. Thank you for the great talk. When using online LLM models for reasoning during training and testing, how did you ensure the model consistently provided answers in a fixed interpretable format? Example, move to XXX, place XXX on XXX for subsequent processing.
For what project was this? For body channel thought?
Yeah.
I assume so, right? Because that's the only part where you talked about these specific intermediate reasons.
Yeah, so I guess this is asking about, I guess it's asking about how we do the corrections. So when we do the deployment, and you roll out the reasonings, and if you see that there is like one of these reasonings that might be wrong, like the human operator can essentially correct this in natural language, but then we ask ChatGPT to format that correction in kind of the structured reasoning way that we use for those reasonings. Yeah.
So maybe that's a related question on the embodied chain of thought. Great talk. Thanks a lot. The validation, the backwards validation of like, you have these intermediate language, but also visual thoughts that you could use to, yeah, exactly, you could use to identify. How much have you spent now time on doing the inverse validation? Like, meaning the actual robot actions properly and accurately represented what the embodied chain of thought was actually predicting? And or do you have the tool chain even in place for the inverse validation?
I see. Yeah, that's a great question. And this actually depends a little bit on how you train the model. In this scenario, like in this paper, we usually trained like with the fixed set of reasonings and actions. So because it's an autoregressive, it's kind of like first needs to predict this, then this, then this, then this, and then the action. If you do it this way, then it will pretty surely like learn to follow this reasonings. But you might also want, if you think that like one thing that is not so good about this is that you don't want it to be reasoning all the time, right? Because this also introduces more tokens that you need to predict at test time, which kind of hinders your control frequency. So one way that you can go around it is to try to do like the training more adaptive. So you can try to, for example, use dropout, like instead of always doing all reasonings, then introduce like this regularization. But if you do that, then it's like more unclear if the action prediction will follow that closely the reasonings that you predicted before.
Yeah.
Yeah.
But if it's recursive, wouldn't that automatically with a high likelihood mean that, let's say in this example, the action over there is obviously quite related to the last step on the visual reasoning
Yeah.
side, but likely less related to the original sub-task description. I mean, it's hard to quantify this in terms of correctness.
Yes,
but-
it's hard to quantify also for a different reason, and that is of how you generate the annotations. Because how we do this in this project is that we essentially use existing foundation models to annotate our offline robot data. But now, because we don't have really ground truth data for these bounding boxes, etc., and reasonings, there is also some level of noise that we are introducing, which is difficult to quantify. So I assume that some percent of our data is wrong, like it's probably like wrong reasonings, but like it's it looks like the foundation models are like, if you tune them, they work good enough that the model can also handle like some noise. But yeah, that's also like difficult to quantify. Yeah.
So for this particular project, do you do the prediction with a chain of thoughts like online, on like how often do you do it, or you just do it at the beginning and then it's kind of like open loop?
Yeah.
Like
So
I imagine it takes like with all the like sum and all the bounding boxes and all these things, like it takes time to all these things. So maybe the control frequency was like super low.
So, I mean, like SAM and this stuff you use offline to generate the reasonings. So essentially, you can view this as some sort of distillation of like the knowledge of like foundation models in other areas into your like VLA policy that now can also kind of reason about like vision and language and other kind of things. And your question was about the control frequency, right?
Yeah, because like this idea, I think it goes kind of in the opposite direction of like doing high frequency.
Yeah. Yes, so that's correct. And when we first started doing evaluations for this project, so this was based on the OpenVLA architecture, which is a 7 billion parameter model. And the first evals were painfully, really painful, really slow. We were doing like 2.5 hertz control with this Widow X. And this was then like Michael, who was an intern in our lab, and William championing this evals in the robot lab, and it was super painful. But then because as I said, because we are now transferring by formulating robotics as a multimodal sequence modeling many advancements from LLMs and VLMs, a few weeks later we were able to compile our model with kernel RT, which is a package from NVIDIA to speed up inference of this kind of large models. And then we were able to do 5 hertz control with all these reasonings for like the same tasks. Having said that, as I said before, ideally, I think you don't want to be reasoning all the time, especially as you go towards like more dexterous, high frequency, maybe humanoid robots. I think the ideal framework is to do like some sort of like system 1, system 2 kind of thinking or architecture, where as long as you are doing in distribution tasks, that you rely on well-trained, really fast policies to do like your tasks. But whenever you have your policy is facing an unfamiliar situation or is unsure about what it should be doing next, then you trigger this and ask it to think more like, oh, I'm not sure what to do, and then you do like this kind of like test time and compute scaling. Yeah, on the back.
Thank you for the nice talk. I have a question regarding cross-former.
Yeah.
In one of the result page, you show that your generalist policy outperformed your specialist policy. I wonder what is your,
Either matches or outperforms.
Yeah,
It doesn't always outperform.
yes. I wonder what is your insight about this? Is this something that we should try to push for, that in the end we have generalist policies that tries to outperform the specialist? Because this is still something that I think is not that very obvious in vision, and also like can be quite counterintuitive in real life, because we don't actually have like a generalist person that can outperform at least some of the specialists in that special task.
Yeah, I think it depends on like the complexity and the dexterity of the downstream task that you care about. I think in cross-former, you know, like we had like some dexterous manipulation tasks, like the bimanual sushi cutting, etc. But I would not claim that, you know, like everybody should just, you know, do this and out of the box it will magically work. What I do think is that if your application requires like very, you know, very high robustness and success rate, you know, like other like requirements, because maybe it's like industrial requirement or something. What I think is that this line of work should enable you to train a strong backbone of like a robotics foundation model that then should be like a really good initialization to achieve like really robust success rates in your like particular downstream task. Yeah.
And so with the simpler, my question is, did you at any point try like the real to sim to real kind of strategy? Okay.
No, we didn't.
Do you think the same recipe could be used for something like this?
Maybe. I think like in simpler, because we were mostly interested in getting correlated evals. We are not like, we have like this pairwise like correlation, but not really like absolute, right? And so like the sims we are using are not like super perfect or super high fidelity in that sense. So I think if you want to transfer from sim to real, maybe you need to like invest more in your sim actually. That would be my guess, but I haven't tried it.
Yeah,
I think there was one more question there.
Yeah, so I have a question about the action detection part. I believe the common problem with behavioral learning is when you execute action, you get like you might get slightly different response from what you expected.
Sorry, can you repeat that?
So like you might get a slightly different response from the robot from what we predict, like the action that you predict. Is it like the common problem in behavioral learning? Like I wonder, do you have that problem when you in any of these projects, and does it affect like
So getting wrong predictions?
No, it's like when you predict action and then it gets executed by the robot, it might get like a little bit different than what the model expected.
Oh, you mean like if there's any drift, like by trying to follow these actions?
Like you see any like you see that as a problem in any of these projects, or like you deal with them?
I see. I mean, like it depends on the project. Like we use different control schemes, like for like the more like single arm control, like the widow X and stuff. We you know, predict like delta and effector poses, and then there is like a low level controller that uses the inverse kinematics to try to like reach those those poses. And like for the bimanual, for example, we do gen control. So it's like kind of different for every embodiment, but I don't think that, yeah, like any drift coming from the low level control has been an issue for us.
So it doesn't affect any of the chain of thought and stuff.
No.
There are 3 questions on Zoom, but short.
Hi, Oier. Very good talk and very nice research. I really enjoy it. One thing I haven't understood about this specific work is the chain of thought you are using, the one from the LLM, or was it refine-tuned or retrained, keeping the embodiment into account?
So like the original architecture didn't have like any chain of thought. So we took like the open VLA, and essentially like everything is now tokens, right? And so like some tokens are doing like this semantic like reasoning, and others do like this visually grounded reasoning.
My question is, does the chain of thought take into account the embodiment? Because the platform can have multiple shapes and number of joints and so on.
I see.
So when you generate the chain of thought, you need to be aware of your shape, right? Because it can have completely different outcomes. Is this taken into account or not in the chain of thought development?
Yeah. So in that's a great question. So in this particular project, we only tested it with a single embodiment, but I'm actually very excited to try to see if common steps of embodied chain of thought would lead to better transfer across different embodiments. Like, I think if you like just think about like what might be like common steps of reasoning, like maybe like motion cues or something, I believe that this has probably more potential for a transfer than thinking about like the right action representation or aligning like different action spaces, etc. Like that's my hunch.
Very interesting. Another question I have is about cross-form, the results, and maybe other slides I don't remember. I noticed that the performance at the moment of manipulation is around 70%.
Yeah.
So this is more a philosophical question. What is it going to take to reach the like kind of the AlexNet moment, or at least the automotive moment? At the moment, you know, automotive is around the 99%. Okay, what are we missing to get there?
Yeah.
Is this VLM, the use of language, actually the answer to this, or do we need something more?
Yeah, that's a great question. I think there are many different answers for this. For cross-former, so these are two very different models that I presented. So cross-former is like kind of like a vanilla transformer policy. So it's a very small, it has like, I think, 130 million parameters. And essentially, when we were training this on this 900,000 robot trajectories, we kind of saw that the model was sensitive to like the exact data mixture that we were training it on. Like meaning we had to like upsample a little bit some of the target embodiments for which we did not have a lot of data, meaning that the model was probably like underfitting like the data. But we were at the limit of the compute like that we could train a model on. So I think like definitely you would see better transfer if the model would have been larger. And so I think like if you train like a VLA on like cross-embodied data, I think, as I said before, I would be more hopeful that if you do the reasoning, that this would help you like achieve like that success rate. Because I think right now we've been kind of like just scaling the data side, and we will never be able to like have the data that covers every possible combination that the robot will face in the real world. But I think that what actually will transfer is like the reasoning, because that's how we humans do it, right? Like we don't need to like be able to have grasped all the objects in the world to know how to grasp it, but like we reason about how we should grasp it, right? So I think that's why I'm very excited about pushing more like this reasoning models aspect.
My last question is about agility. In one video, you showed the robot with two arms folding clothes, and it was accelerated 8 times. So what does it take to make it work faster than it is now?
Yeah, that's a great question. So I think for like that's kind of like the cool research that there is to be done now, right? Because I was saying like this dexterity and generalization have like a little bit different keys for success, right? And so because now we've been like deploying like large models, this has come a little bit at the cost of like high frequency control. I think there is a lot of cool like research to be done on how we can like speed up like these models by using a lot of like techniques from LLM lands, like maybe like speculative decoding or like better like system 1, system 2 kind of architectures. But that's like kind of like very open like research that, you know, like we are working on right now to try to bridge the gap of like having like good models that can generalize by using like strong backbones, but also like be able to do like up to 200 hertz control if you want to like control like a humanoid, for example.
Or a drone.
Or a drone. Exactly.
Because there you need to be very fast, for example.
Yes.
Yeah.
Yes.
Okay, thank you.
So we are already 10 minutes over time.
Oh,
let's see. There were online questions. Yeah.
3 online questions.
3 online questions.
Yes.
Long ones or?
very long ones. There's one short.
Okay, let's
Maybe
try to,
I can answer over email or something.
yeah, so maybe for the online ones to see if anyone else in the room has questions. The ones online, we just answer them by email,
Yeah.
okay?
That would be great.
Anyone else in the
Any
room?
pressing
Yeah,
matters?
yeah.
I was wondering, so if I understood it correctly, for most of the projects, like, integral part was scaling up the real world data, like this very big data set in the beginning, and being able to train on this different real world data with different robots. And you mentioned this spark moment of this generalized models on this data being better than the specialists. How much of it do you believe is also like just due to having much more data in the real world? And do you believe that you could still have takeaways to also try to produce simulation data, but also in like these different modalities, for example, drones, arms, humanoid robots that would also lead to performance gains?
Yeah, I think that's a really great question. That's also like one question that I've been thinking about like since last summer, but I haven't had like time to explore, which is essentially, so I'm not like sim to real has like definitely like some applications where it really shine. But in general for like, you know, I don't know, like general manipulation and so on, it's kind of like difficult to get everything right. But the promise of like scaling up sim data, I think I would be very interested to see if we essentially not do sim to real, but co-train. If we like co-train on real world data as we have been doing now, and also have like sim data, like during pre-training, like what can we learn from the sim data? What can we extract from sim data? Like, is this a good way to scale the performance? And I think like that's a difficult but interesting question to answer, because with this high capacity networks, you know, as the sim data and the real data look very different, if you just do naive co-training, there is nothing that stops the network from just fitting like the different modes. Like it probably could like be really excel at whatever sim benchmark that you co-train on, and then also learn how to do like real world like behaviors, but don't transfer, right? So I think like there is the question of if you do this, like, you know, maybe using like semantics or like some of the techniques I showed for like the heterogeneous sensor data might be interesting to look at, essentially to how to force that there is transfer from sim to real.
Thank you.
Yeah.
Okay, go ahead. Last question.
Well, thank you very much for your time. I was wondering, you mentioned that one of the ideas to improve speed in reasoning based control methods is by having some kind of system one, system two structure. Currently, you're using a transformer based like kind of default architecture for like all the problems of the world right now, right? If you add this kind of like a few systems or like a few components, this kind of you have to kind of design how this looks like, and these components will interact in a non like how would I say this? They're like just designed explicitly to interact in certain ways instead of having more fluid connections between them. For example, you would have like one model to let like your model know when to think, one model which would do the system one thinking, one model to do system two thinking, for example, right?
It could also be all one model.
All one model. So how would that kind of look like in your mind?
I think we can chat about this offline maybe.
Okay.
I think it's like a longer conversation.
Okay.
All right, thank you very much. Let's give a hand to Oier.